includes installing your problem.
Okay, good. Oh, it does. All right. So, all right, this is microservices, hardware accelerated network microservices. Actually, thankfully, I really can go quickly because this was upstairs. Basically, microservices, as everyone knows, are the next step, I think, in service decomposition for scaling. A lot of times they're referred to as network microservices, but really just running in in containers or on devices. Our network microservices we envision really running in the network hardware. And so that's why I'm talking about the hardware accelerated versions of these. Basically, we think about things that can focus on packets, packet at a time sort of behavior. And so by combining intelligent networks that allow us to redirect streams to processing elements, a rich set of network processing elements in using network processors or in FPGAs, we really have a new way to sort of program the network. And that's the way that we are thinking about implementing these network microservices, but in a way that extends potentially traditional stream-based computation, so that it works well with the cloud and is able to. We can think about it as just sort of extending the computation out over the network. So you saw, maybe some of you saw actually a couple of the FPGA platform that we had upstairs. It's a newer version of this. We've been working with FPGAs for a number of years. FPGAs in the communication data path, because one of the problems using FPGAs as an accelerator is getting the data in and out. If you think about having an FPGA in the communication path, the data is already flying by. So that problem is essentially solved. They're all over the place. Intel bought Altera for $13 billion. Xilinx, Xinx, Mellanox, who owns the top of the top 500, has an FPGA platform. Arista has an application switch that's used in high-frequency trading, low-latency trading. So FPGAs are sort of all over, and we're thinking more about them as a way to implement an optimized service rather than a prototyping platform in the way that they used to be thought of. The first thing that we did was offload collective communication onto the FPGAs on the NIC. So MPI, collective communication, which can be, we focused on MPI, although collective communication appears in other processing platforms. But anytime in distributed memory, when all the nodes need to communicate, there's a potential bottleneck. And so we targeted that in MPI to begin with. We made it really easy by having thinking about this as a bump in the wire, so the FPGA can be in the switch or on the NIC. We have some that are sitting in the host, but actually a distinct NIC that is routed through. So anywhere you can put programmable logic in the network data path, you can implement these things. We initially implemented it by thinking about just packets, and you send a UDP packet to initiate a collective. The NICs communicate amongst themselves, compute the collective answer, send a single release packet, and things go much faster. There's the packet. There's an architecture. There's a little instruction processor that has very simple instructions that it reads from the packet, and understanding what MPI operation to perform, and it's much faster. So these are speed ups. These are actual run times, minimum and average. The minimum and average of the programmable logic are right on top of each other because the variance is very low. You don't have any of the operating system noise. So we win with the all reduce. With actual applications, this is an application that has a lot of buy-in from the physics department here that does things that I won't even dare to explain, but with an actual application, we saw as much as sort of 40% speed up in application runtime. The other aspect that we're looking at microservices is from the edge computing perspective. So the goal here is to support stream processing of sensor data in a way that would connect together seamlessly with something like Twitter Heron. And in fact, that was sort of our model. But we want to be able to run these on small embedded platforms in the network with a single sort of execution model, or a single basically limited execution functionality. Given that we don't run arbitrary programs because of stream processing, it looks like this, sort of with simple operations, simple task pool. This can run on a microcontroller, so it doesn't need a full operating system. and it's designed again to run inline in the network. The implementation that we just submitted to IEEE Edge, hopefully not the fake one, hopefully the real one, shows that this really is 23,000.
Dennis is in charge of it.
Yes, yes, that's what I hope it's the real one.
I'm writing your reviews right now.
Okay, good. 23,000 times speed up. I mean, 27. This, I mean, basically being able to process these things in programmable logic as the data is flowing by versus this is the C reference implementation running on the same device is incredible. I mean, and so as long as the execution model is limited, you can program simple operations on a stream of data. You can think about things as a packet at a time. And this is using IoT, CoAP, and CBOR encoding. So we're hopefully doing the right thing with IoT streaming. The speed up is incredible. The drop rate is also incredible. This, the x-axis here is decorated with these little stars because the programmable logic never drops packets, even though the other reference implementations, even the C reference implementation, as we increase the packets per second into the millions of packets per second, starts to just fall over. Programmable logic never falls over. So as long as you have a reasonable execution model, streaming data, you can implement incredibly efficient network microservices and in a way that's good. So we're looking in the future at thinking of a collective operation in MPI as being just another instantiation of a stream-based processing option. We were talking about sort of collectives in a streaming world just yesterday, and we're hoping to merge these two models in an under 5-minute talk.
Are you going to bring mine up?
Yes.